My name is Lior Poplingher, and I will present our analysis of the different flutter mechanisms that the Benchmark Supercritical Wing experiences as part of the third elastic prediction workshop. The Benchmark Supercritical Wing is the current test bed for the third elastic prediction workshop. The focus of the workshop is set on evaluating the flutter onset boundary of the BSCW at a transonic Mach number of 0.8 and high angles of attack. In the experimental work of Dansbury and others on the BSCW, the flutter onset dynamic pressure sharply decreased as the angle of attack was increased, as you can see in the figure. It was also noted that the flutter mechanism changes from 2 degrees of freedom heave pitch flutter to a stall flutter dominated by the pitch frequency. Stall flutter is caused by negative aerodynamic damping due to stall in parts of the aeroelastic motion. The goal of the current study is to investigate the physical properties of the stall flutter mechanism of the BSCW at high angles of attack by coupled U1's aeroelastic simulations. Our test case is the Benchmark Supercritical Wing that was experimentally tested by Dansbury in NASA's transonic dynamics tunnel. The structural modes of the wing are pure heave at 3.3 Hz and pure pitch at 5.2 Hz, as you can see in the right figure. You can see the computational mesh in the left figure. We focus on a single Mach number of 0.8, and we examine two angles of attack of 1 degree and 5 degrees to study the different flutter mechanisms of the BSCW. We use the Easier Flow solver, which is a finite volume structured Navier-Stokes solver developed by the Israeli CFD Center. We use the Spalater-Maras turbulence model with the Edwards and Chandler's modification and the mixing glare correction. Regarding our simulation approach, we start with a steady-state simulation at a given Mach number, angle of attack, and dynamic pressure. This is used to initialize the flow fit. Next, we perform a U1 simulation with the dual time-stepping method using the time step of 0.1 milliseconds. Finally, we perform a full dynamic aeroelastic simulation in which we don't use any sort of initial excitation and don't subscribe any structural damping. We technically give the wing a kick resulting from the transition from rigid wing simulation to elastic wing simulation. We want to compute the aeroelastic system properties, and we do so by using a system identification process called multi-output autoregressive model, or MOA. We use the model displacements combined, that is a vector psi, to identify the system properties. The autoregressive part means that we assume that we can describe the response at time n by a linear combination of responses at previous p time steps, which is the MOA order. The identified system parameters are the frequencies and damping of each aeroelastic branch of the system, so we can also learn about the stability of the system at different dynamic pressures. Additionally, the MOA coefficients, that is the elements of the matrices AK, signify the contribution of the J model response at time n minus k to the I model response at time n. The A11 and A22 terms account for the effect of Xi1 and Xi2 on their own time histories. The cross terms account for the cross effects of the heave and pitch on each other. Based on the magnitude of the Aij elements, we attempt to characterize the different flutter mechanisms by examining the mutual effects of the heave and pitch time histories. We start with the identification of the stall angle of attack for the BSCW configuration at Mach 0.8. We show here the steady lift coefficient of the BSCW at Mach 0.8 for the rigid configuration at two different dynamic pressure values that differ slightly in the Reynolds number, which is the source of the difference between the two curves. The linear trend breaks between 3 degrees and 4 degrees angle of attack. So, all the simulated aeroelastic responses at 5 degrees angle of attack and Mach 0.8 are practically at stall conditions. Now we examine the aeroelastic responses at the lower angle of attack of 1 degree. Our roadmap is to show the aeroelastic response and fit an autoregressive model to extract the dynamic properties of the system and try to gain some physical insight on the flutter mechanism. In this slide, we can see the time histories of the heave and pitch displacements at 1 degree angles of attack for several dynamic pressures. For the lower dynamic pressures, the response is stable, while at 172 psf on the right, the response is initially diverging in both heave and pitch. As the response develops, the heave displacement reaches an LCO, while the pitch continues to diverge. The change in the heave displacement trend is associated with the increase of the total pitch angle above the stall threshold, which bounds the aerodynamic forces. Since our objective is to study the BSCW's different flutter mechanisms, in the following slides we consider only the initial diverging phase of the response at 172 psf. The aeroelastic system parameters were obtained using the MOA model. You can see in this slide the frequency and damping as function of the dynamic pressure for 1 degree angle of attack. As shown earlier, at 172 psf, there is an unstable aeroelastic branch with negative damping, and the response is diverging. From the frequency variation, we observe that at pre-flutter conditions, as dynamic pressure increases, the frequency of the pitch aeroelastic branch is decreasing. Based on the coalescence of the frequencies of the two aeroelastic branches, we conclude that the BSCW experiences a conventional 2-DOF Heave pitch flutter at this angle of attack. Finally, we show here the elements of the Moore coefficient matrices for different time lags at 1 degree angle of attack and 172 PSF. As expected, the overall contribution decays with increased time lags. The larger values are on the diagonals, indicating that the displacements are mainly affected by their own time histories. The A12 term is larger than the A21 term, indicating that the pitch motion is driving the heave motion, while the heave has only a minor effect on the pitch. Now we continue to the higher angle of attack of 5 degrees and follow the same roadmap as before in order to analyze the distinct flutter mechanism at this condition, which is above the stall angle of attack threshold as we've seen earlier. In this slide, we show the time histories of the heave and pitch displacements at 5 degrees angle of attack for several dynamic pressures. The system is unstable for all dynamic pressures presented, and the flutter onset dynamic pressure is significantly reduced compared to the 1 degree case. The pitch displacements clearly diverge while the heave only slowly grows. In the heave response, we can identify two different phases. First, we see the response to initial condition at the heave natural frequency, and as the pitch oscillation's amplitude grows, the aeroelastic forcing becomes more dominant and the amplification at the pitch frequency also grows. We again use the Moore model to obtain the aeroelastic system parameters. You can see in this slide the frequency in damping as function of dynamic pressure for 5 degrees angle of attack. Based on the negative damping values, we obtain that the pitch branch is unstable for all simulated dynamic pressures, as we've shown earlier. In contrast to the lower angle of attack, the frequency variation is minor, and overall the pitch branch frequency remains close to the pitch natural frequency. We show here the elements of the Moore coefficient matrices for different time lags at 5 degrees angle of attack and two dynamic pressure values of 50 and 100 PSF. Similar to the 1 degree angle of attack case, at all dynamic pressures, the larger terms are the diagonal ones. That is, the displacements are mainly affected by their own time histories. The off-diagonal terms indicate that the pitch displacement has a larger effect on the heave displacement than vice versa. It is noteworthy that for the lowest dynamic pressure of 50 PSF, which is the closest to the flutter onset, the effect of the pitch displacement on the heave response is dominant, even more than the effect of the heave time history itself. Based on the previous results and the stall threshold at Mach 0.8, we identified that at 5 degrees angle of attack, the flutter mechanism is that of stall flutter, characterized by a dominant response at the pitch frequency. In this slide, we show the pitch displacement and force responses on the left, and the connection between them at 100 PSF using the Lissajous curve shown on the right. Based on the inclination of the curve and its orientation, there is a phase lead of the pitch force with respect to the pitch displacement. The phase lead contributes to the negative aerodynamic damping at these conditions, which introduces energy to the system in each cycle. In this slide, we show the development of the zero friction coefficient contours on top of the pressure distribution on the upper surface of the BSCW throughout a single pitching cycle at 5 degrees angle of attack and 100 PSF. The title of each subplot indicates the current position along the cycle. Throughout this flutter cycle, the wing experiences stall. A significant portion of the boundary layer on the wing's upper surface is separated. In the upstroke, the shock location moves upstream while strengthening, and the separation extent grows. As the total pitch angle begins its downstroke, the separated region further increases, even though the total pitch angle decreases. So we can see that the separation extent lags the pitching motion. This delay between the pitching motion and the separated region contributes to the phase difference between the motion and the aerodynamic loading, and to the negative aerodynamic damping. To conclude, we performed the aeroelastic simulation of the BSCW at Mach 0.8 and 2 angles of attack. At 1 degree angle of attack, the BSCW experiences conventional 2-DOF heave pitch flutter, while for the higher angle of attack of 5 degrees, which is above the stall threshold of the BSCW, the wing experiences stall flutter. Using system identification of the aeroelastic system, we found that at the higher angle of attack, the pitch displacement has a significant effect on the heave displacement, that is, the aerodynamic response is the main driver of the flutter mechanism, while at the lower angle of attack, it is the coupling of the displacement that drives the invertibility. Analysis of the flow separation on the BSCW at the higher angle of attack revealed that the separation extent lags the pitching motion, leading to a phase difference between the motion and the aerodynamic loading, and consequently to negative aerodynamic damping that drives the stall flutter mechanism.